Hi, welcome all to CE for Civil Engineering classes. So in this session, we'll see the slope deflection method which comes under the structural analysis. So slope deflection method is generally a method of finding or analyzing and the indeterminate beams as well as the frames. Now, I can call the slope deflection method as a part of a displacement method. So we all know that in structural analysis, to analyze structures, there are broadly two methods. That is, you can have force method as well as there are displacement methods for analysis. So the detailed force and displacement methods we can learn in yet another video. Now, the slope deflection equations and this method comes under the displacement method of analysis, just like the Canny's method, moment distribution method, etc. Okay, and now to start with, this particular method was introduced by Professor J. A. Manny in 1915, and the method says that if the slope at the ends as well as the displacement at the ends are known, then the end moments can be calculated in terms of the slope deflection stiffness as well as the length of members. That is, if you consider a particular structure, you'll that is consider a fixed beam with certain loading, already it will be having a fixed end moments developed, and due to loading also the final end moments developed can be calculated by making use of this particular equations. So before moving on to how this method is or what is the equation, we need to know about the assumptions which was made in making this equation. So the assumption made was, first of all the joints were assumed to be rigid. That is, see, consider a frame ABCD, and if I'm considering ABC, a certain joint B is considered, and say some deformation is made to this B such that this is B dash C dash. So we can see that the central angle remains the same. That is, there is no angle deformation is not occurring. So this joint is considered to be rigid. Again, the second second assumption is that distortions due to axial deformations are neglected. Like for example, in this beam itself, like for example, sway moment is coming, and so here if the beam sways, it sways as a whole. That is, the deflection here will be same as that happening here also. So the delta here will be the same. So that is the whole idea. And the final assumption was that all the shear deformations were neglected. So the deformations due to the bending of flexure was more predominant in comparison to the shear deformation. So that was neglected. So these were the assumptions made in this equation. And moving on to the equation, we need to find out what all sign conventions were being used. So this is very important to understand the sign conventions when it comes to actual application of the equations to the problems. Okay, now the clockwise end moments were considered positive and anti-clockwise end moments were taken as negative. Like for example, in this figure A, B, C, D itself, say consider this joint B. Here, the moment at BA, you can see that this is clockwise in nature. So you can write MB as positive, whereas MBC, this is anti-clockwise in nature. So you write it as a negative. Anti-clockwise was negative and clockwise end moments were taken as positive. Then regarding rotation, the clockwise rotation of tangent to elastic curve is positive and anti-clockwise rotation is taken as negative. Like here, you can say it is a clockwise rotation, you take it as positive. Anti-clockwise rotations were taken as negative. Okay, then here you can say this one again, this will be the anti-clockwise rotation, so this will be negative and here it will be positive. Now settlement, regarding the settlement, delta is positive, or the settlement is taken to be positive if the right side support is below the left side support. Like we see in this beam ABC, say take portion AB. Here the deflections, the delta in AB is taken to be what? Positive, because here the B is below the A, that is right side support is below the left side support, so you take it as positive. And in case of beam BC, you can say that the left side support, that is B, is below the right side support because B is sinking here, right? So we take it as negative. So if delta is 7 mm, you will write it as plus 7 mm in case of delta AB, and delta BC will be minus 7 mm. For example, now this is the final slope deflection equation. So if you take a particular beam, say fixed beam is considered, AB is the beam, and say B is deflecting by an amount delta, you can write the final end moments is given by the fixed end moments m of AB plus 2 ei by L plus 2 theta A plus theta B minus 3 delta by L. Or you can write the fixed final end moments is equal to the fixed end moment plus 2 ei by L into the 2 times the rotations at the near end. That is, AB is taken, A is the near end. If BA is taken, B is the near end, plus rotation at the far end minus 3 delta by L. That will be the equation. L is the length of the beam under consideration. Okay, so here the terms MAB denotes the final, MAB, MBA, they will denote the final end moments, MAB, MBA respectively. M of AB, M of B are the fixed end moments at ends A, B respectively. EI is what you call as the flexural rigidity. So many objective questions, this has been asked. What is EI? EI is called as a flexural rigidity, modulus of elasticity into moment of inertia. Theta A and theta B in this equation denotes the rotations at the end A and B, and delta is the deflection. So on a final note, I can write the end moments as fixed end moment plus 2 ei by L into 2 times the slope at the near end plus slope at the far end minus 3 delta by L. So in the options you can find such forms of this equation also. So this also has to be known. Now, so before we go on to the problems, we need to know how to calculate this fixed end moments, and this is of very much importance when it comes to objectives and other exams, or whatever we have to apply this particular equation, we need to know about how to calculate the fixed end moment. So you can learn it for different kinds of beams. We can learn the equations. So first one is a concentrated load which is not at the center. We can write M of AB is WAB square L, WAB square by L square. M of BA is given by WBA square by L square. Now next is concentrated load at the center. The equation is given by M of AB is minus WL by 8, because here the load anti-clockwise moments in the sign convention was taken to be negative. Now in the clockwise, say if this is A and this is B, the clockwise rotation, here the moment is taken to be positive, so M of BA will be positive. Similarly, for in the case of a uniformly distributed load, fixed end moment is given by plus or minus W L square by 12. Now in the case of uniformly varying load, from one end, say this is taken as AB. So M of AB is minus WL square by 30. M of BA is WL square by 20. So these are equations we have to know how to do this particular or solve this particular kinds of equation by this method. Now in the case of a uniformly varying load, from both ends we have minus 5 by 96 WL square plus 5 by 96 WL square. And finally, with a beam with a moment, central moment, this equation is of much importance. That is, M of AB is given by M into B into 3A minus L by L square, and M of BA is given by M into A into 3B minus L by L square. Or the fixed end moments can also be written in the form of this is another equation for M of AB. M of AB can also be written as M into B into 2A minus B by L square, and M of BA can be written as M into A into A minus 2B by L square. So these are the equations for the fixed end moment. So these are the basic things we need to know about the slope deflection equations. So the further the application of the slope deflection equations in the problems, in the equations, etc., we can see in the upcoming parts of the classes. So thank you all for watching CE for Civil Engineering. If you like the videos, please like and subscribe the video. Thank you.